In this and subsequent videos, we would like to talk about parametric curves, define them, and discuss some of their properties. The relevant sections are 10.1 and 10.2. So to begin with, let us think about graph of a function. So say we have the graph of y equals f of x for some function f. So what this could look like is, say, the following. If we graph this function, we could obtain something of the sort like this. And so this would be y equals f of x. Now, this being a graph of a function, it must pass the vertical line test. So whatever is the function that we graph, it must pass the vertical line test, which says the following. If you take a vertical line like so, then it can intersect the graph of your function only at one point, say here. It will never intersect the blue graph in 2 points, regardless of which function f you take. So of course, this imposes a restriction on the types of graph that you can get. So for example, something that you cannot obtain as a graph of a function could have the following form. So you could have something that clearly does not pass the vertical line test. It may even have self-intersections and so on. Now, the primary question I want us to answer right now is, why would we even care about objects like this? So this is something that clearly does not pass the vertical line test. In the sense that there are a number of ways to draw a vertical line so that it will intersect this curve, this black curve, in more than one point. Still, it may be interesting to consider objects like this for the following reason. So think of it as trajectory of an object, right? So think of a plane. We fix the system of coordinates in the plane here, and we have a particle that moves along this path, right? So it will move, say, in this direction. So at different points in time, it traverses all of these positions. And of course, this being a particle, it certainly can intersect its own trace. So you have a particle tracing this path down, then at some point it may intersect and intersect its own path and return to this position one more time. There is no issue with that. So in other words, we would like to handle curves that describe positions of an object in the plane as a function of time. Right, so this position of an object in the plane will depend on time. So the way to do this is we want to think of the coordinates of our point in the plane. So say we have a point in the plane which traverses this path. So these are the coordinates of the particle. Then, as we mentioned already, these coordinates depend on time. At different times, the particle occupies different points x, y. In other words, both x and y somehow depend on time. So think of x, y as functions of time. So this is the distinction between the curve as we know it, the one that we're used to, where it consists of the points with coordinates x, y. Right? So what is this? This is all the points x, y such that y is a function of x. Now, what we want to think of here with parametric curves are the points x, y such that both x and y depend on another variable, time. And so we think of this here as the graph of such dependence of coordinates on time. And so we will say that a pair of functions x of t, y of t defines a parametric curve. In the sense that if you take these two functions and trace them in the xy plane, treating t as time, you will obtain trajectory of certain object moving in the plane. And so this is the definition of a parametric curve. In other words, here, to define the usual curve, we need a single function. And the single function gives the dependence of y on x. Now, for parametric curves, we need two functions, which will describe the dependence of x on time and the dependence of y on time. So, of course, any usual curve is parametric. So if we have a curve y equals f of x, say, this is a curve, then we can think of it as a parametric curve by saying, well, okay, let us just say that x is our time and then y depends on time. So this gives us a parametric curve. So any standard Cartesian curve can be thought of as parametric if we agree to say, well, x is precisely time. And then as time goes by, our particle traverses this usual curve. So, in other words, parametric curves is a richer, is a more broad class than the usual curves that we are familiar with. So let's talk about some examples to illustrate this concept of a parametric curve in detail. for the first example, take the unit circle. What do we know about it? Well, the unit circle, as it is used to define sine and cosine, can be thought of as follows. So we know that for a point that corresponds to the angle, say t, right? So we have the 0 direction in the direction of the x-axis, and if we measure the angle t counterclockwise, like so, right, so this angle is t, then the projection of the point on the unit circle onto the x-axis as coordinate cosine t, and projection of this point onto the y-axis as coordinate sine t. In other words, if we think of points of the unit circle as parameterized by the angle t, or if we think of angle as time, so somehow our particle is rotating around the circle as the time goes by, the angle increases. So we are saying that effectively the angle and the time are one and the same. So as time goes by, our particle circles around, making more and more turns. The x-coordinate of this particle is given by cosine t, and the y-coordinate of this particle is given by sine t. And this is just from the definition of the unit circle. So this is from the definition of the unit circle and how it is used to define sine and cosine of t. So of course you can verify that a point with these coordinates for any t between minus infinity and infinity lies on the unit circle by doing the following. So verify that the point with coordinates cosine t, sine t is on the unit circle, like so. If we think of cosine t at the first coordinate, sine t at the second coordinate, we can just add them up together, square them and add them up, like so. We have x squared of t plus y squared of t is cosine of t squared plus sine of t squared. So that of course gives 1. In other words, we have just verified that if we take any point xy where x and y depend on t in this fashion, then we have x squared plus y squared equals 1. And this of course is the equation of the unit circle. So this gives an independent verification that such points lie on the unit circle. So of course we knew this in the first place because we knew it from the properties of the unit circle and from the way it defines cosine and sine of t. But this provides an independent verification. So the takeaway is that the parametric curve x of t, y of t equal to cosine t comma sine t, or in a different notation, this could be written as x of t equals cosine t and y of t equals sine t, like so, in a system with t being any real number. So any such point lies on the unit circle. So this is the parametric equation of the unit circle. And so t corresponds to the angle. As t increases, the particle that has this parametric equation goes round and round and round the unit circle. If t is increasing, it goes counterclockwise. If t is decreasing, it goes clockwise. Just as we know from the way sine and cosine are defined, increasing angle corresponds to counterclockwise direction and decreasing angle corresponds to the clockwise direction.